So hello, everybody. It's Nicholas Palumba, and I'm here with Joe to present our microgrid design project. What we're going to talk about is the following items. Specifically, we're going to discuss the specific components that comprise the microgrid system. For introduction purposes, we have the diagram of the microgrid system here. The grid connected PV microgrid system is comprised of several vital components as shown. At a high level, we got the solar photovoltaic system and associated DC to DC converter. We also have the battery system and associated battery charger. These devices are connected to a 1000 volt DC bus, which is also connected to a DC to AC converter, or the inverter. And this inverter provides connection to the local load and grid. So here we have a graph of the load profile and PV generation profile that was provided for the previous year. We're considering a similar facility to the load data that was provided, except we're going to assume that the facility was reduced by a factor of 10, so that the use of the power conversion block was not necessary, so that the power flows would make a little bit more of an intuitive sense. So as such, we got the load profile here and for a year. And as you can see, the maximum expected load is about 14 kilowatts. And same story for the PV generation profile. We could see that the maximum expected PV generation is 50 kilowatts. Here we have a schematic of the modeled PSCAD grid interconnection. And for our case studies, we used resistive loads to model different load values. So for example, if we wanted to model a 50 kilowatt load, we used a resistance value of 4.6 ohms. The grid impedance values are given by 0.1 ohms and 0.1 millihenries. Here we have a schematic of how we modeled the solar PV system and associated boost converter in PSCAD. So the solar PV array is sized for a rated power output of approximately 50 kilowatts, and it also uses the SunPower SBR X21 345 modules, which are each rated at 345 watts at standard test conditions. So the boost converter is sized to have an output power to the DC bus of 50 kilowatts. And taking a step back, the way we sized our solar array was we had 10 strings of 14 PV modules each for a total of 140 modules, which comes to about a power rating of 48.3 kilowatts. And the way we sized it that way was to get the maximum voltage possible into the boost converter to consider I squared R losses. We wanted to maximize voltage as compared to current input to the boost converter. And we also on this slide have the standard formulas for boost converters for sizing the inductor and capacitor in order to meet the specified output ripple, which was 50% output current ripple and 1% output voltage ripple for an operating load at 50 kilowatts. So on the next slide, we have how we modeled the control system, and we have the transfer function for the boost converter circuit, as well as the compensator that we designed to meet the desired output characteristics. These parameters were evaluated in MATLAB using the Bode diagram and the typical stability characteristic requirements to ensure stability. Okay, so the next component is the the battery and battery charger system. This is how we modeled it in PSCAD. The individual battery modules that were selected, right, are rated at 48 volts each and 10 amp hours each. And we also sized our battery for a 12-hour duty cycle of off-grid operation, particularly during the nightly period of 6 p.m. to 6 a.m. And we simply size this by sizing the system for at least 600 kilowatt hours, which is 50 kilowatt hours times 12 hours. And we also included an aging factor for the battery of 1.25. So assuming that over time the battery reduces to 80% of its original capacity, and a 1.1 design margin factor for additional conservatism. We designed our pack for a total of 825 kilowatt hours. And as such, we also designed the battery input to be 1,104 volts. So that comes out to 23 battery modules in series and 92 strings in parallel. So we had a lot of batteries in the system, over 2,000. We also have the standard equations for sizing the inductor and capacitor for a buck boost circuit. And as you can see, we got 27 millihenry for the inductor and 60 microfarads for the capacitor to achieve the desired output performance requirements. Here we have a model of the charge control. It's slightly different between grid connected and island mode. And below you can see the transfer functions that we derived for both the buck boost circuit and the compensator required to achieve the desired performance requirements. And as you can see, the grid connected version of the controller has an input that shows the desired current input or output to the system. On island mode, the system is simply controlled to ensure 1,000 volts on the connected DC bus. So on the next slide, here we have how we modeled the bidirectional inverter. And we got the equations for sizing the different passive components, right? We got the capacitor on the DC side and the capacitor on the AC side, as well as the inductor on the AC side. And on the next slide, here we have what we modeled in PSCAD for the grid connected version of the control for the inverter, which is rectifier control. And we have the controller for both the voltage loop and the current loop on the left or the right there. And here we have how we modeled it for island control with the transfer functions on the right for the associated system.